Why do people go bald?
Why are baboons' bums red?
What's a light year? Why do leaves go brown in the autumn? Why do monkeys like bananas? Why do some things glow in the dark? Why do animals not understand you? Why do my receipts fade after a year?
Don't know the answer? Ask the Naked Scientists.
Hello and welcome to this week's Ask the Naked Scientists with me, Sue Marchant, Dave Ansell and Chris Smith. Great question, first of all, from Gary. Can you ask Dave, wind can affect sound, but does it affect light?
If the wind is kind of turbulent, and so you get some places where the air is slightly expanded and some places where it's compressed, that can affect light, because when air expands, light goes through it slightly faster than when it's compressed. So you can actually see this effect much better if air is heated over a stove or over a toaster. You may have noticed that stuff behind the toaster kind of looks all wiggly, and you get sort of weird distortions behind it. You get this kind of transparent waves going up above it. That's because the air is expanded when it gets hot, and so it bends. It's called refraction. It's a bit like when light hits a piece of glass, it often bends and ends up coming in a strange direction, so everything looks distorted. And so wind could have a very, very slight effect on light in that way, because some bits are going to be compressed and some bits expanded, and it might sort of make everything look slightly distorted, very, very tiny amount. It's not going to drag the light with it in the way that sound gets dragged with wind, because light travels through the vacuum, through the space, rather than through the substance. If you shout to someone who's downwind of you, the sound travels much better than shouting upwind,
yes,
because the sound is travelling through the air itself, and if the air's moving, then the sound's going to move with it. So it's going to go with the air towards the person downwind, so it's going to be a lot easier. But because light moves in the vacuum and the vacuum isn't moving, then it's not going to move in that way. So it will have some effect, but not nearly as strong a one as on sound.
Thank you very much. Gary, I hope that's helped you out as well. Now, June from Braintree would like to know, how long does it take for a body to decompose?
It varies, actually, upon the conditions in which the body finds itself. So if you look in the Arctic, for example, there are people that are buried in the permafrost who died in the 1918 pandemic of flu, the Spanish pandemic, and those people are still up there. In fact, they're in such good condition, some of those bodies, that scientists have been able to get back from their bodies the genetic sequence of the flu virus that killed them and piece it back together again. So those bodies are in ideal conditions. It's very cold, and because it's so cold, it's completely dry, and because it's so cold and dry, bacteria, which would normally break down a body, and fungi and other microorganisms, cannot function, and so the body is preserved. Taking it to the other extreme, if you put a body in very warm, wet environments where microorganisms and also things like flies and maggots can get into a body, then it can break down very, very fast. And scientists do experiments with things like sheep and pigs, which have died, and you leave them in various environments and monitor how quickly these changes kick in and how quickly various insects get onto the body and lay their eggs and that kind of thing. And this is the basis of forensics, actually. And under those circumstances, bodies can be gone in a week or so. And you just have to look at a rabbit that's been run over or something, and other things fly in and start pecking at it and pulling it to pieces. There's not a lot left within a week or so in warm weather.
One of the stunning thing, of course, is that we've seen in Egypt, they've opened King Tut's tomb and, put it in a specially acclimatised place so that people can view the mummy. That is really quite stunning, isn't it?
Yes, it is. And I remember when I must have been about 10 years old, looking at this Egyptian mummy, and it was open to the air, and you think, well, this is several thousand years old. It is incredible, and that's the power of mummification, because the Egyptians knew all about how to preserve things, and they knew, for instance, they were one of the first peoples in the world to explain and to demonstrate that silver is very good as an antibacterial agent. So they used to put bits of silver in their drinking water because they knew that if they did that, they wouldn't get infections. And so we now use silver. In fact, there's several companies have got patents out on spraying silver as a fine powder into a surface so that the surface slowly leaches tiny amounts of silver over time. And it's the perfect antibacterial surface. And so people are now looking at coating the insides of fridges like this and even the operating tables in hospitals because it cuts down infection. But we've got the Egyptians to thank for that.
Right, OK. Now then, we've got a live caller. We've got Jill from Ipswich. Good evening, Jill.
Hi, Sue.
Let's have your question then, Jill.
I was in Cornwall a couple of weeks ago. I saw a beautiful sunset. And then when I come back to Ipswich, I see the same sun. And then I thought to myself, how do we see the sun, that same sun, all over the world?
So your question is sort of, although the world's a ball, how can we all see the sun if it's always on one side of the Earth?
Yeah, I do realise that the Earth is round.
The trick is that the Earth is spinning. We can't all see the sun at the same time because half of the Earth is at night time at any one time. So while we're in the daytime, Australia's at night time.
Yeah.
But as the Earth turns round, all parts of the Earth will point towards the sun at some point for half of the day, roughly, for half of 24 hours. And so that at some point they're going to be pointed towards the sun so we can see it.
Yeah, but, like, I'm in Ipswich right now.
Yeah.
Okay, it's night. Just pretend it's daytime. I can see the sun.
Yeah.
But if I'm at the same time in Norway, I know the hours change a little bit.
Yeah.
But I'm in Norway, I can still see the sun.
Yeah, because Norway is actually, compared to the size of the Earth, it's quite close to us. It's sort of maybe only a 24th of the way around the Earth away from us. If you went all the way round to Australia or Japan, then during the day here, you wouldn't be able to see the sun in Japan or Australia.
It might be worth bearing in mind here, Jill, that the sun is millions of times bigger than the Earth. You can pack 1 million planet Earths inside the sun. It's huge, and it's also 93 million miles away, which means that from a very big bit of space, you can see it. And so you don't actually have to go very far across the surface of the Earth, and it's still the same sun, because compared with the distance the light has had to come from the sun to get to you, and compared with the size of the sun, between here and Ipswich or here and Devon is a tiny distance. So you're not going to see a sun that looks hardly any different at all from that kind of distance.
And yet in Norway, or like the other side of the world, we can still see that same sun, can't we?
Yes, that's right, because it's so big. And it's also a long way away, so it's a bit like you looking at something in the distance and wandering from one side of your bedroom to the other. You're still looking at the thing in the distance. It's still the same thing.
What about the countries which are in dark 24 hours a day, like 6 months or so?
Well, the Earth isn't actually straight upwards, downwards, north-south. Most people think of the Earth as going through space with the North Pole at the top and the South Pole at the bottom. But it's not quite like that, because the Earth is a little bit tipped over. In fact, it's inclined at an angle of 23.5 degrees. So that means that for roughly half the year, we're pointing towards the sun, and the other half the year in the Northern Hemisphere, we're pointing away from the sun.
Yeah.
And that coincides with the fact that we have longer days in summer and shorter days in winter, and it tends to be warmer in summer because more light is hitting the Earth and warming it up, and in winter less light is hitting the Earth. Now, if you're right on the top of the Earth, in the North Pole, when the Earth is on that part of its orbit around the sun that the North Pole is pointing away from the sun, it's perfectly possible for the sun never to get above the horizon for you, so it never gets light. It's dark. And then when summertime comes and you're on the part of the Earth's orbit where the top of the Earth is pointing closer towards the sun, under those circumstances, the sun never goes below the horizon, or almost never. So that's the land of the midnight sun, and you have almost continuous daylight.
Okay.
All right, thank you, Jill. Bye.
Bye.
Now then, a regular caller and somebody who's always wanted to ask our scientists something is Tony from Westcliff. Hello, Tony.
Hello, lovely to hear you again.
Lovely to hear from you. What's your question?
Well, it's this. I think it's Dr. Dave, you like this. I want to know how the sun was actually formed. Where does it come from? What is it composed of? And why is it hot?
Okay, the sun, it's mostly made up of hydrogen. It's about 94% hydrogen, about 6% helium, and then there's a couple of other odds and ends, which are much less than 1%. It's sort of iron and all the things which the Earth is made out of. It's made up of partly from just gas, which was left over from the Big Bang. It's in an area where there's a whole lot of hydrogen and helium gas kind of gently grouping together under gravity, sort of falling together under gravity. It's also got slightly more heavy elements than it would have, so things like iron and oxygen, things like that, than you'd get just from the Big Bang. So astronomers think that they came from supernovae, which are old stars which have got really, really old, and then they kind of suddenly collapse under their own weight and then explode back out again. And that makes heavier elements, and everything heavier than iron, so they think that the sun's got some of that in it as well. And basically it was this big gas cloud, and then slowly over millions and millions of years it kind of collapsed under gravity. And when you compress a gas, it gets hotter. I don't know if you've ever pumped up a bicycle tyre and noticed that the bicycle pump gets hotter and hotter as you do it.
Yeah.
Well, that's the same thing as you compress all this huge billions and billions of Earth's worth, it's probably millions of Earth's worth of gas and billions of tons collapsing under its own weight, it gets hotter and hotter and hotter. So that's how it got hot in the first place. But it would have just cooled down over probably a few 100 million years to start with. But then once it gets really, really compressed and got really, really hot, the hydrogen inside it starts to react with other hydrogens in a nuclear reaction. It's the same nuclear reaction which powers the hydrogen bomb. And they fuse together to form helium atoms, and that releases a huge amount of energy. And that's what the sun is running on. It's a huge nuclear reactor turning hydrogen into helium. It should run for sort of 10 or 12 billion years at least, as it is at the moment. So it's used about half to a third of its life so far.
That's really interesting.
I think I can shed a little bit more sunlight on this for you.
Right.
What we know about this was recently massively improved or enlarged upon by the discovery of an interesting meteorite, because there's a group of Danish researchers from the University of Copenhagen, and they were looking at the composition of ancient meteorites. Now, what people thought happened to create our solar system was that there was this massive cloud of gas. It was roughly 100 astronomical units in diameter. That's 100 times the distance between the Sun and the Earth. And since the Earth and the Sun are 93 million miles apart, you can work out pretty quickly that that was a pretty big ball of gas.
Yeah.
Now, the question about how it actually got kick-started, people thought what had happened is that there was another star, pretty big, sitting nearby our present solar system in space about 4.5 billion years ago. That star blew up, and it sent through space a big shock wave, and the shock wave was what was responsible for pushing on this big cloud of gas and making it begin to fall into itself, and then under its own gravity it fell into itself harder and harder and harder, and was also spinning, and this created the Sun. That is a plausible theory. It certainly probably works in some other solar systems elsewhere in the universe, but in this case, when they analysed these meteorites, they found that it just didn't add up. Because what they were looking for was the evidence of that massive explosion that would have created that. And when a star blows up, as Dave says, they've got a lot of iron in them. And what they were looking for in these meteorites was a form of iron called iron-60. Iron-60 is a radioactive form of iron, and it turns into another breakdown product called nickel-60. So they analysed these ancient meteorites, thinking that they would see this signature of the explosion that created us. And they couldn't find it. But what they did find was something called aluminium-23, and aluminium-23 is a form of aluminium that's produced in the surface shell, the outer coat, or the outer layers of a star, which is huge. Stars which are about 40 or 50 times bigger than our own sun produce in their surface layers lots of aluminium-23, and they also give off this wind. And the wind is a sort of million-mile-an-hour maelstrom of charged particles and aluminium-23. So this means that they've now refined their model of what we think happened in the early stages of the formation of our solar system. And they think that this massive star produced this huge wind which blew into our cosmic neighbourhood, hit this ball of gas that was going to become our sun, and buffeted it at just the right rate to cause it to begin to collapse on itself. And so we had the help of this other star to create the sort of collapse event that then culminated in the birth of our sun. And as this stuff gets more and more compacted and makes the sun, and it's all spinning, it begins to pull all of the material around it into a flat disk called a protoplanetary disk, a bit like the rings of Saturn. And then that dust and debris in that disk begins to cause the aggregation of other dust and debris and bits of material and starts to form planets. They're called planetesimals, and then they join together to make bigger planets, and off you go. You've got a star system.
Good God.
Wow. Fantastic.
Can I just say one last thing? Why is the sun, and for that matter planets, actually round like footballs? Why should they be so even?
Basically because gravity, every part of them is attracting every other one, and they're all trying to get as close together as possible. And the sphere is a shape which means they can all get as close to each other as they possibly can. I mean, in the same way as if you've got something at the top of a mountain and let it roll down, it's trying to get closer to the most of the Earth. So everything's trying to get as close to each other as possible, and the best shape for that's a sphere.
Very interesting, and thank you very much.
Thank you very much.
Thank you, Tony. Bye-bye.
Bye-bye, dear.
Now, Alan, Alan, sending hugs, says, I have a question for your scientist, Dr. Dave. If two small vessels containing equal volumes of water, one at 2 degrees and the other at 9 degrees, are placed in a freezer set to minus 18 degrees, which one will freeze first and why? He's asking this because he's heard that the warmer water will freeze first. Why is this? Good question, Alan.
Yeah, there is definitely a lot of talk about. I think it does happen if you boil water and let it cool, then try and freeze it. It'll often freeze quicker than the normal water that you've just taken out of the tap and put in the freezer. I'm not sure whether that would be true of water which has only been at 9 degrees centigrade versus 2 degrees centigrade, because the cooler it is, the less energy it's got to lose, so it should freeze quicker. The explanation for why boiled water freezes quicker could well be that water normally has a lot of gas dissolved in it. If you ever leave water in a cup for a long time and it warms up a bit, you see little tiny bubbles of gas in it. That's a sort of dissolved oxygen and dissolved air, basically, coming out of solution and forming little tiny bubbles. So when you've got a lot of gas dissolved in water, it probably makes it harder for ice to form. So the water might have to get slightly cooler than it would do with pure water to dissolve. Also, when you heat up water, especially if you boil water from around here, it will take out quite a lot of the dissolved limestone, which is why our water's so hard. It's got a load of limestone dissolved in it, basically, and if you boil it, it takes some of that out, so you've got even less things dissolved in it. So it is possible that water which has been heated up, which has been boiled, could freeze quicker than normal water. I think probably if it's just tap water at 9 degrees centigrade and 2 degrees centigrade, probably the 2 degrees centigrade would freeze first. What do you think, Chris?
There's one other theory which was put to me by an atmospheric chemist the other day, and he said he'd read somewhere that when you make a big bucket of hot water and a big bucket of cold water, ignoring the effect that Dave has just suggested, which is very important because when you boil water, all the hardness, and particularly the temporary hardness, comes out. That's the stuff that furs up your kettle element. But when you put hot water in a bucket, you get convection currents, and this is where something warm rises in the same way that hot air rises. Smoke goes up a chimney. And so this sets up a current in the bucket where you have warm water from the base of the bucket rising up towards the top. It gets a bit cooler because the top of the bucket's open to the air, and then the colder water drops back along the edge of the bucket, and this sets up a sort of circulation inside the bucket, a bit like a current. And some people have argued that when you put the warm and the cold water side by side in your freezer, there's more movement already in the water that's hot than in the cold, and this makes it a more effective heat loss system. So it's better at losing heat faster, so the hot water can overtake the cold water. Now, if you add that effect into the effect that Dave was saying, then you can see how this might translate into, under certain conditions, more rapid freezing of the hot water. But it's a myth, or an urban myth with perhaps some evidence behind it, that's gone on for donkey's years, and it's created more kind of argument scientifically, I think, than virtually any other problem.
Right, OK, let's hope that helps. Now then, we've got Bill from Cambridge. Hello, Bill.
Good evening.
Hello there, you're through to Dr. Dave, Dr. Chris.
Thank you, yeah.
Hi, Bill.
Hello. No, I was interested to hear you talk about aluminium-23. For several years, and especially about 12 years ago, I spent a lot of time picking up aluminium cans. And I read somewhere a few years ago that the world consists of about 8% of aluminium. Is that right, or what?
The most abundant element on Earth is oxygen. That makes up about 60% of the mass of the planet. Then I think after that is silicon, and that's about 23% from memory. Then you've got things like iron. Iron's about 6% or so. I think aluminium's probably around about the 6 to 10% mark as well. So aluminium is very, very abundant in the crust, but it's not aluminium metal, and therein lies the problem. Aluminium's a wonderful substance because it's an excellent conductor of electricity. It's very light and very strong, and in fact electricity cables are made of aluminium because copper's very expensive, but it also stretches and breaks. Aluminium, much lighter, much stronger, ideal choice for cables. Problem is that getting it out of its ore, its ore is bauxite, and that's aluminium oxide, Al2O3. To get it out of its ore costs an enormous amount of energy, and the way you do it...
This is what I learned. I mean, my understanding is that around about 100 years ago, aluminium was worth more than gold.
Well, it almost still is. It's one of the most energy-intensive metals to recover.
Yeah, well,
and that's why you're encouraged to recycle it, because to get it back from its native form, its form bound to oxygen, bauxite, you have to put the aluminium into an electrolysis chamber. Now, what that means is you heat it up to about 1,500 degrees Celsius, and then with electrodes made of carbon, you pass a huge electric current through the ore, and this pulls away the oxygen, which forms oxygen gas and reacts with the carbon electrodes to make CO2. You also get some other gases like fluorine produced, which is not very nice, and you get molten aluminium metal, which you then tap off. But the amount of electricity is huge because you have to do this with electrolysis.
Yeah, so there's a very good case for recycling, isn't there?
Exactly, because when you recycle it, it takes a fraction of the amount of energy.
I had some aluminium cans. I lit a fire on a kind of a makeshift furnace. And I actually got a galvanised bucket and I melted some aluminium cans down, you know. And it wasn't that difficult, you know.
Well, that's right. Melting the aluminium once you've made it into metal is very easy. And
I think it melts about 660 degrees, isn't it? Is that right?
It's not. No, the melting point isn't very high for aluminium. But getting it out of the ore, you've got to melt the ore, you see, and the melting point for the ore is very high. And the process needs a lot of electricity to do it. So it's much better to recycle than to recover new aluminium from the ore.
There's a great question here, which is something I've often wondered about. It comes from Janet in Northampton, and she says, can you tell her why, when she's been travelling in the car for a couple of hours at night and then go to bed, does she still get the feeling that she's still travelling? I get this as well.
I think it's a bit like it's sea legs. You can get aeroplane legs. When I took a very long aeroplane flight back from Australia earlier this year, for about the first few hours after I got off the plane and then laid down, I was convinced I was still airborne. And I think it's all to do with the way in which the part of the brain that registers how you're moving in space is wired up. Now, the way in which we sense our balance is a system called the vestibular apparatus, and inside our ear, attached to the inner ear, the part of the ear that translates sound waves into electrical signals the brain can understand, is this vestibular system. And there are a series of tiny canals. They're just 5 millimetres across, and each one about 0.5 millimetre in diameter. And these canals are arranged in a sort of circle, and they're in the X, Y and Z axes. And what that means is they're all at 90 degrees to each other. So one of the canals is arranged so it's like a halo going around your head, and that can detect whether you're turning your head from left to right to look over your shoulder, for example. Then there's another one of these circles which is orientated like an upwards hoop going from front to back, and that can detect nodding movements of the head. And then there's another one which is like a circle going from one ear to the other, and that can detect side-to-side movements of the head. And inside these tubes is a kind of fluid. And when the head moves, the fluid gets left behind transiently by the movement of the head. It's got inertia. And so the fluid pushes onto some hairs that project inside these tunnels, these small canals, and it distorts or deforms the hairs. And this triggers the hairs to trigger nerve cells to send nerve impulses to the brain. So the brain can work out what direction your head and your body are moving in. And these signals get fed to another part of the brain which tunes up how you respond with your musculature to those movements. Because whenever your body moves, it means that you're changing your centre of balance and your centre of gravity. And in order to compensate and stop you from falling over, you have to adjust the behaviour of different muscle groups to compensate. So if you're standing on a boat deck and the boat is rocking backwards and forwards, you have to trigger your muscles to exactly and precisely compensate for that movement so that you don't fall over. And the same thing happens to your eyes. If you were to not move your eyes, whenever you moved your body at all, then the visual world would go all over the place and you wouldn't be able to see anything. So your brain continuously resets itself and adjusts how it responds to the world to balance out the world for you. So if you go on a long journey, if there's a certain movement in that journey which is continuously occurring to your body, your brain learns to ignore it because it's continuously compensating for it and it doesn't want to keep telling you about it. It's a bit like you're not conscious of wearing your underpants. I know maybe you are, but most people aren't. And that's because the brain learns to ignore things that are present all the time, continuous stimuli. So when you then take yourself away from that continuous stimulus, suddenly the thing that your brain's been cancelling out is no longer there. And what was a positive plus a negative equals 0, now you've got a positive, no negative, equals a signal. And the brain suddenly is sensitive to the fact that this thing that it was cancelling out is now gone. So you start feeling it again. It starts automatically almost generating a phantom of the thing that you've been cancelling out. So that's why you have these sort of sea legs.
because I've noticed this before when I've been on a boat for 2 or 3 days, and what felt like was happening to me was that normally when you stand up you make all sorts of little tiny movements just because you can't quite stand up straight, and then normally if you're on the ground you assume that that's you moving, but when you're on a ship you assume it's a ship moving, because otherwise you'll get very, very confused. And then when I came off the boat, it felt like I was assuming that all these little tiny movements were the world moving rather than me moving. And so it felt like I was still on the ship. Would that make sense, Chris?
Sounds good, Dave. Yeah, I mean it's pretty much the same thing, isn't it? You're ascribing a movement to something that's not coming from you to a movement that is coming from you, and you have learned to cancel out the one that was coming from elsewhere. So you now think that all these movements are because you're still moving, and it's in fact you're generating them.
Is that how painkillers work then, Chris? They cancel out that signal going?
Painkillers a bit different. A lot of people say, why or how does aspirin work? How does it know where the pain is? Which is obviously a very sensible question to ask. But the answer is that something like aspirin or paracetamol don't just home in on the hot spot. What they do is reduce your sensitivity to pain right around your body. And it's not that suddenly pain switches off everywhere. It's that when you have an area of the body that's injured, you produce chemicals in that part of the body that make your nervous system there much more sensitive. And what aspirin and other anti-inflammatories do is they block the production of those sensitizing chemicals at that site, which is why the pain goes away when you take an aspirin in those areas. It's not that the aspirin is homing in on the diseased area, it's that it's blocking that effect everywhere and stopping the nervous system becoming sensitised wherever there's an area that's troubling.
Right, Chris from Basildon would like to know how the outside temperature when you're in a plane can be so very low as it is much colder than it ever is on the ground, when in fact you're nearer to the sun.
You are nearer to the sun if you're in a plane, as long as you're flying during the daytime. But it's a tiny, tiny effect. Chris was talking about earlier that the sun was sort of 80 or 90 million miles away. And when you fly up in a plane, you're maybe 6 or 7 miles up. Yeah. So that's so you're a little bit closer, but only a minute amount closer. But you've got a lot less insulating atmosphere above you. So it's a lot easier for the heat to get back out into space the higher up you get, which is one of the bigger. So the heat. So you've got the same amount of heat coming on you effectively, but it's a lot easier to lose heat. So everything gets colder. There's also an effect that if air rises from down on the ground where it's really quite warm, 20, 30 degrees centigrade, as it rises, it expands. And so we were saying earlier that when gases compress, they get hotter. When they expand, they get colder. And so as they rise, they expand and get colder. So once they get up to the altitude of your plane, they're actually really quite chilly. So basically 2 effects. One is that if air rises, it expands and gets colder. And the other one is that there's less insulating atmosphere above you, so there's less to keep you warm.
That's it for this week. Our doctors will be back with me next week for more Ask the Naked Scientist. But don't forget you can also catch them on the Naked Scientist podcast, which you can find on the Naked Scientist website, www.nakedscientist.com.
The Naked Scientists are sponsored by the Wellcome Trust, the EPSRC and UK Fast. For more information, look us up online at nakedscientists.com.